In this section, we're going to talk about some of the basic calculus that we can do with vector-valued functions. The definition for the derivative of vector-valued function looks very similar to that of what we learned in Calculus 1 for a real-valued function. R prime of t is equal to the limit as delta t approaches 0 for r of t plus delta t minus r of t all over delta t. Now, in Calculus 1, you might not have used delta t. You might have used h or something similar, but really this is just the difference quotient. And if we calculate the limit as this tiny distance between our 2 points gets close to 0, that will give us our derivative. So because this is practically the exact same limit or derivative definition that we learned in Calculus 1, we can continue doing derivatives exactly the same way we did in Calculus 1. And now for vector-valued functions, since our vector-valued function is going to have multiple components, since they are separated with pluses and minuses when we have them in IJK format, we also know that we can calculate derivatives of terms individually. So we really can just evaluate these derivatives component-wise. That just means take the derivative of each component individually and put them back together for your final answer. So in math symbols, what this means is if we've got r of t is x of ti plus y of tj plus z of tk, r prime of t is going to be a vector-valued function with just the derivatives for each of those component functions. So x prime of ti plus y prime of tj plus z prime of tk. So these derivatives are the exact same types of derivatives we would take in Calculus 1 because each of these individual component functions is its own kind of self-contained function of one variable. So we can think of r of t as a position vector. If you were to plug some value in for t, what we would get is an xyz position that some object is located in a path at a particular time. So the original r of t function we sometimes considered a position vector. What that means is that r prime of t, if r of t is position, then r prime of t is going to be velocity or tangent vector. The magnitude for r prime of t represents just the speed, which is the magnitude of velocity, and then r double prime of t represents acceleration. We will look at these applications of derivatives in depth a little bit more in the next section. For right now, we're just going to calculate or practice calculating them. So first example, let's let r of t equal ti plus 2t plus 3j plus 3t squared minus 5k, and we want to do some calculations with this vector-valued function. So the first one is r prime of t. So all we have to do is create a new vector-valued function whose components contain the derivatives of the original vector-valued function. So for our I component, the derivative of t is just 1. For the j component, the derivative of 2t plus 3 is just 2. And then for the k component, the derivative of 3t squared minus 5 is 6t. So r prime of t is 1i plus 2j plus 6tk. So we can still have variables in here. This derivative still can be a function of t. So r prime of t represents velocity, which has two components. It's got a magnitude and a direction. The magnitude for r prime of t is speed. So if we were to just apply our magnitude formula to what we got for r prime of t, remember magnitude is when we go in and just square each component and then add them together under a square root. And we just simplify this as much as we can. We work out those squares. We have 1 plus 4 plus 36t squared. So we get 5 plus 36t squared. So this function right here, it's not a vector anymore because we did magnitude. Remember, magnitude is a scalar. So this function can tell us what the speed of our particle is at any particular time t. We can plug in a time and it tells us what our speed is. For r double prime of t, just like in Calculus 1, the way we get the second derivative is by taking the derivative of the first derivative. So we've got to refer back to part A and just take the derivative one more time. So we get the derivative of a constant is 0. So the derivative for 1 is 0 in our I component. The derivative of 2 is 0 in our j component. And the derivative for 6t is just 6 in our k component. Now, those zeros are optional. You can write them if you want to see all three of your standard unit vectors, but if you don't, we could just say this is the same as 6k. Now just some more practice. We will be doing some in-depth calculations with our derivatives in a couple of sections. So just some practice right now of the calculation. We'll talk more about what these mean a little bit later on in a different section. But for part D on this example, we want to calculate r prime dotted with r double prime. Keep in mind what operation you're performing and what your answer, your final answer should look like. Remember, the answer to a dot product is not a vector, it's a scalar. Because these are functions of t, when we say it's a scalar, that doesn't mean we have a guarantee that we have a numeric answer back, but it guarantees our answer is no longer a vector. But we could still have t's, like we saw back in our speed in part B where we did r prime of t, the magnitude. It is no longer a vector, but there still are variables in the answer, and that's fine. So what we're doing here is r prime, which has components 1, 2, and 6t, and we want to dot that with r double prime, which had components 0, 0, and 6. So remember, with dot product, we're multiplying corresponding components. So you're going to multiply the I components together, you're going to multiply the j components together, and you're going to multiply the k components together, and then we just add those products. So that's 0, that's 0. All we get is 36t for r prime dotted with r double prime. One more calculation real quick. We're going to do r prime cross r double prime. Again, remember, the answer to a cross product is a new vector. And the way that I like to calculate these is with a 3x3 determinant matrix. R prime came first in that cross product, so I'm going to put its components in row 2, which are 1, 2, and 6t. R double prime has components 0, 0, 6. So if we work our cofactor expansion here, remember we need to start with I. You start with the first character in the first row. You're going to mark off its row and column and ignore them. And what we're left with is this 2x2 matrix. And the way that we calculate the determinant of the 2x2 matrix is we calculate the products on the diagonals and subtract. So for I, we're going to have 12 minus 0 if we do those diagonal products. 2 times 6 is 12. 6t times 0 is 0. When you jump to the next position in row 1, we change the sign so it's minus j. If you cross off j's row and j's column, the 2 by 2 matrix you're left with has diagonals of 6 and 0. Change sign again when you jump to k, and our diagonals are 0 and 0. So r prime crossed with r double prime gives us 12i minus 6j. And you could write plus 0k if you want to, but it's not required. Okay, so pretty straightforward derivatives. The only thing you need to keep in mind is if our vector valued function has 3 components, that means we're going to have to take 3 derivatives. And derivatives are used to help us define whether a vector valued function is smooth or not. So a curve is smooth on an open interval I if x prime of t, y prime of t, and z prime of t, those are the derivatives of our component functions. If they're all continuous on I, and r prime of t is not 0 for any value of t in the interval I. So the only way that r prime of t will equal 0 is if all 3 components equal 0 at the exact same time. So there's a few things that we need to check when we want to decide if our curve is smooth. A curve that's not smooth would have a discontinuity or a cusp. And a cusp is just a sharp spot. So let's try one of these. We want to find the intervals on which r of t equals e to the t, t squared minus 1, and 3 is smooth. So there's a few things that we need to check. A curve is smooth on an open interval if the derivatives of our component functions are all continuous. So let's first look at our component functions and their derivatives. X of t is e to the t. X prime of t is e to the t. The derivative for e to the t is e to the t. E to the t is continuous on negative infinity to infinity. E to the t has no discontinuities whatsoever. It's a nice, smooth, continuous curve. Our y component here is t squared minus 1. Its derivative is 2t, which is just a straight line. It's got no discontinuities, no holes, no jumps. Our z component is just 3. Z prime, since z is a constant, z prime is 0, which technically, again, is just a line. So it's continuous from negative infinity to infinity. But that's not all the work we need to do. So far, all we've confirmed is that x prime, y prime, and z prime are continuous everywhere. We also need to make sure that all of the components don't equal 0 at the same exact time. So we need to know where each of these equals 0. Well, e to the t never equals 0. Which means r prime of t can never equal 0. If you've got a component that can never equal 0, then you're fine. We will always have a value in the x of t position, so r prime of t will never equal 0. Just for completion, we're going to check our other components. We want to know where 2t is going to equal 0. If you divide both sides by 2, it's at t equals 0. And then we want to know where z prime of t equals 0. Well, it's equal to 0 always. But because this first one will never equal 0, that means r prime of t, the vector valued function overall, will never have 0, 0, 0 as the components, because this e of t will always give us back a non-zero value. So technically, r of t is smooth on negative infinity to infinity. We confirmed that all of our derivatives of our components were continuous, and they are. And then we checked to make sure that they won't all equal 0 at the exact same time, and they won't. The last thing we're going to talk about in this section is integration. Just like our derivatives, integrals are defined using limits. Therefore, integrals can also be calculated component-wise. There's one trick, though, we need to be really careful with. If we're going to calculate these integration problems one component at a time, we're technically performing multiple integrations. So the integral for r of t dt would be the same thing as doing the integral of your x of t component. Our answer is still a vector, so that's going to give us our component for I, and then we have to do the integral of y of t for j, and the integral of z of t for k. So the way that we've broken this down now, it looks like 3 different integral calculations we have to do. And because of that, each component is going to have its own arbitrary constant. And there's several ways that we could write this. So let's look at an example, and I'll show you the different ways that we could include that arbitrary plus c in each of the components. We want to evaluate the indefinite integral. That means we're not going to be plugging any values in for t, for natural log of ti plus 1 over tj plus k with respect to t. So we need to calculate the integral for natural log of t dt, and that will give us our I component. And then the integral for 1 over t dt, and that will give us our j component. And there's nothing in front of the k, so we could just imagine that there's a little coefficient of 1 there. So we need to integrate 1 for our k component. So you may remember back in Calculus 2 how to integrate natural log, or you may not. The integral for natural log technically requires us to work out integration by parts. And when we do that, we get t natural log of t minus t. And then we say plus c sub 1. And I'm saying c sub 1 because I want to use c for all of my arbitrary constants, but there's no guarantee that all of those arbitrary constants will have the same value. So we need to do something in order to distinguish between them. So for my I component, I've got arbitrary constant c1. The antiderivative of 1 over t is natural log of absolute value of t. And that is a separate integration problem, so it gets a separate arbitrary constant, which I call c sub 2. And then the antiderivative for 1 is t, and then plus our third arbitrary constant, and that's our k component. So this is one way to represent our antiderivative with those arbitrary constants. You may also see those arbitrary constants pulled off to the side in their own separate vector. So I sometimes see this as natural log of ti, doing my antiderivative. So t natural log of t minus ti plus natural log absolute value of t j plus tk. So those are all the functions we got back from the antiderivative, and then we could also have a c1i plus c2j plus c3k. So I've sometimes seen it written like this. I prefer this way that I boxed, because when we actually use this for some calculations later on, it's going to be nice to have those arbitrary constants in with those functions and only have to work with one vector. So the second way, it's like we've got 2 separate vectors. For our next example, we're going to do a definite integral. And what that means is we have values to plug in. We still, with definite integrals, work this out exactly the same way. We need the antiderivative for each component, but we do not need arbitrary constants when we're doing a definite integral. So we're going to start by taking the antiderivative for each of those pieces. The antiderivative for t is 1/2 t squared, and that is our I component. The antiderivative for t cubed is 1/4 t to the 4th. That's our j component. And then cubed root of t, we need to think of that as t to the 1/3. That way we can work our power rule on it. So the power rule for antiderivative said add 1 to your power, so it's going to be t to the 4/3, and then we flip that new exponent out front as a coefficient. So it's going to be 3/4 t to the 4/3 k. And this needs to be evaluated at 1 and at 0, and then we subtract. So if I plug 1 in for all of my t's, I'm going to get a 1/2 I. Now be really careful, this is still a vector. I get 1/2 I plus 1/4 j plus 3/4 k when I plug in 1. When I plug in 0, I get 0i, 0j, and 0k. So we're really not subtracting anything. But if we needed to, remember we can perform addition and subtraction component-wise as well. So you could take the I component here, the I component here, and combine them with the subtraction. And we do that for each of them if there were some non-zero values in that second vector. But when we do all these subtractions, we're just subtracting 0 every time. So we're left with what we had when we plugged 1 in, which is 1/2 I plus 1/4 j plus 3/4 k. I see a lot of mistakes in this type of problem because in Calculus 1 and Calculus 2, we're used to always having an answer that's a constant when we do definite integrals, because we're replacing all of the t's with actual numbers and then combining. So that's still happening here. We're still replacing the t's with numbers and then combining the results, but it's still always going to be in vector format. The only thing that gets rid of a vector is when we calculate dot product. The answer to a dot product will be a scalar, and when we calculate magnitude, the answer to magnitude is also a scalar. All the rest of these calculations should still be vectors. So I've got one more example that I want to show you, and this kind of foreshadows what we're going to do in our next section when we talk more specifically about velocity and acceleration. What we are given here is that r double prime of t is -4 cosine tj plus 3 sine tk. And we want to find r of t. We know r double prime. We want the original r. So that would tell me I need to get rid of those two derivatives. Well, the way that we get rid of derivatives is by calculating antiderivatives. But we don't have any limits of integration to plug in. So these are going to be indefinite integrals to go from r double prime of t backwards to r of t. So what we've also been given are some initial conditions. We know what r prime of 0 is, and we know what r of 0 is. So this is going to help us along the way to solve for those arbitrary constants. So if we take the derivative of r double prime, it will give us r prime. Excuse me, antiderivative. If we take the antiderivative of r prime, it will give us r. So this is a two-step problem, two major components to it. And once you see the first part, the second part is just do it all over again. So we need to start with the antiderivative for r double prime, and that will take us back to r prime. Now be really careful with this r double prime. I'm noticing that there's only two components, but it's a j component and a k component. If you want to, you can insert an I component and it would technically be 0. There are no i's in R double prime, but it's possible that some i's will appear when we do antiderivative, so we need to keep that in mind. Just because we don't see it in one derivation of the R doesn't mean it doesn't exist in the original R. So we want to integrate 0i minus 4 cosine tj plus 3 sine tk. So we're just going to take the antiderivative of each term individually. The antiderivative of 0 is an arbitrary constant. So I've got c1i. Now, if you have subtraction in between any of your terms, I suggest you change it to addition and keep that minus sign with that cosine term. So think of that not as subtract 4 cosine t, but add a negative 4 cosine t. And the antiderivative for cosine is sine, and the coefficient just carries along. So antiderivative for negative 4 cosine t would be negative 4 sine t plus some arbitrary constant. And by keeping that negative with that first term, we're not confusing ourselves with the minus out in front and trying to decide if it needs to be distributed to both of them, which can get confusing sometimes. The antiderivative for 3 sine t is negative 3 cosine t, and then we have another arbitrary constant. So this is our preliminary R prime. But there are a bunch of arbitrary constants in here. So if I assume that this is my R prime, I know that R prime of 0 should come out as 2i minus 3k. So we're going to plug 0 into our antiderivative. That's plugging 0 in for the t's. When we do that, we get c1i. Sine of 0 is 0. So we also just have c2j. Cosine of 0 is 1. So we've got negative 3 plus c3k. So this we're able to figure out from our antiderivative. But according to the information we were given, R prime of 0 should be 2i minus 3k. And by setting them equal, we will be able to solve for those arbitrary constants, because we could solve this equation term by term. So what this means is that C1 has to equal 2. C2 has to equal 0 because there are no j's in R prime of 0. And then negative 3 plus C3 has to equal negative 3, which means C3 is also 0. So now we know for certain what R prime of t must be equal to. So I'm going to go back to my antiderivative and I'm going to plug in the values I find for my arbitrary constants. So we figured out that C1 was 2. So this is 2i. C2 is 0, so this is just minus 4 sine tj. C3 was also 0, so it's just minus 3 cosine tk. So that's one full iteration of the process that's required for this problem. Now we need to do the whole thing over again to go from R prime back to the original R. And you're going to do the exact same steps you just did. To go from R prime to R, we need to take the antiderivative. So we need the antiderivative of 2i minus 4 sine tj minus 3 cosine tk. So the antiderivative of 2 is 2t plus c1i. The antiderivative for negative 4 sine t is going to be positive 4 cosine t plus c2j. The antiderivative for negative 3 cosine t is going to be negative 3 sine t. plus a C3 in our K component. And we were told, well, this is our preliminary R of t. It's not our final answer because it still has arbitrary constants in it. So remember, back at the beginning of the problem, they gave us some information about R of 0. So we can use the answer that we found and plug in 0 and compare it to what they say we should get, and then we could use that to solve for the arbitrary constants, and we'll have our final answer. So if we plug 0 into our antiderivative, 2 times 0 is 0, so we just get C1i. Cosine of 0 is 1, so we get 4 plus C2j. Sine of 0 is 0, so we just get C3k. And all the way at the beginning, they told us once you have what you think is the original R function, R of 0 should equal 4j. So we can compare what we have so far, and this is supposed to equal 4j, and we can match up like terms. The j component on the left-hand side needs to equal the j component on the right-hand side. And that's true for all of the components, which means C1, well, there's no I on the right. That means C1 has to be 0. 4 plus C2 has to equal 4, and that means C2 is 0. And then there's no K on the right, which means C3 has to equal 0 as well. So we're finally ready to finalize our answer for R of t. I'm going to go back to my most recent antiderivative and replace my arbitrary constants. We just found that C1, C2, C3 were all equal to 0, which means our final answer is 2ti plus 4 cosine tj plus negative 3 sine t k. And you could write that as add a negative, or you could write it as subtraction. It doesn't matter. They're the same. Okay, so it's a pretty long process. All it is, though, is antiderivatives and some algebra. And you go through that whole process twice because we're trying to undo two derivatives. Now, we're going to do another one just like this in the next section when we start talking about projectile motion and acceleration and velocity.